everyone. So today I have my friend Alpha, and he's putting me through a more advanced dynamic programming interview. So should be fun. Last time we did some of the classic ones, so today we're gonna ramp it up.
Yep. So yeah, we're gonna do 2 to 3. And then second or third question, I kind of have some different ones, and I can ask you what you prefer.
Sure.
So we'll start with this one. Let's see what the okay. It looks like a can paste says.
Cool.
All right, let's go to this one. And so this is actually a hard on LeetCode, but I don't think it's a hard. It's more like a medium. So
Okay.
yeah.
So, all right. Let's just break this question down. Let me move myself to the middle. So, is audio fine, by the way?
Good for me, but yeah, I'm just listening to you on like the Google Meet thing.
Stream is the everything good on the? Okay, it's good. Sounds good. All right. So we're gonna break down this question. We got the first example. We're given an m by n integers matrix. Return the length of the longest increasing path in a matrix. From each cell, you can either move in 4 directions, left, right, up, or down, and you may not move diagonally. So let me take some notes here. Wait, let me wrap this in like the 3 codes.
Okay.
So I can have my notes here. So yeah, we're given, so this is 1 right here. We're given 9, 6. We'll work through the first example. They're saying the longest, what we're trying to do is grab the longest increasing path. So we just need to, so it's saying the longest is 1, 2, 6, 6, and 9.
Mm-hmm.
Other paths are like 1, 6, 8, but that's 3. And it needs to be strictly increasing, or no?
Yeah.
Okay.
So, yeah.
Needs to be strictly.
Yeah, that also makes the problem easier. So yeah.
Okay. So it needs to be strictly increasing. So it goes 1, 1, 2. So this path doesn't work. And then, yeah, it needs to be increasing. So what I'm thinking right now, so the result here is 4. If this was like 6, the answer would be 3. It'd probably be like 1, 2, 6, or it could be 1, 6, 8, or 1, 6, 9. But it just needs to follow any path. So what I'm thinking is the brute force solution is we would just do a backtracking algorithm. So it needs to be chat. Brute force is a backtracking algo. We're pretty much, we'll loop through every single element in this array. And if we hit a specific, or for every element, we'll try to see for every index, or for every row column pair, we see longest path we can make there, right?
Mm-hmm. And how would we keep track of, in this case, like when we backtrack, how do we keep track of like what we saw already, I guess?
Well, we'll like have a path, and we add to that path. We'll like pretend we start at 1, right? We start at 1. We'll add to the path, and maybe we'll store like a scene, and we'll add the rows and columns to the path of scene. That way, pretend we had like 0 here, and we start at 0, 1, 2, then we get to 6. We don't want to pop 0 back in there anyways. Base. But like, we might not need to worry about that because we know it's less than for sure. If we ever got to this element, we know we're only looking at values that are higher, so it kind of disqualify.
Yeah, like is
neighbors.
it possible to get a loop? Like, is it possible to go in a chain in
Not really if we only recurse based on increasing values. So we might not need a scene set.
And so with backtracking generally, so if you try to get like every path, do you know like roughly the time complexity of that? Like maybe not for this problem, but just like a rough
Probably
time complexity of
it's
backtracking.
definitely going to be an exponential algorithm, but we can probably memorize it. So we can figure out the longest increasing path from every index and
Mm-hmm.
and then cache that. So it'd be like a 2D array. So we'll have a DP row and column, and it's gonna tell us this is the largest or longest increasing for row column
Mm-hmm.
combination. So pretend that we cached it, right? Pretend we've already captured 6 and 9, and we figured out the longest here is 2 if we start here.
Mm-hmm.
Pretend we do 0, 1 and it recurses and it gets to 6. It doesn't need to finish it off. We can just return that the longest path here is 2 and add it to our length of the current path. So we get 3 plus 2 is 5. And then we also store this as well. Like if we do a DP on row and column, that's we know the longest increasing for that specific row and column. We could just early return, and that will sort of speed up the algorithm.
Right. So what would be the time complexity of that? Like if we cache results.
I think it would be around O of n times m because let's see. It will be around. It will be longer than O of n times m, but I don't know how to calculate that because, well, it'll at least be n times m, right? But then we're gonna multiply for each element. We're gonna have to perform that backtracking algorithm, but it won't be that inefficient because it'll eventually cache. So it's there's like a it's multiplied by some t, but I need to figure out how long that t might actually run. Does that make sense?
Okay. Yeah. So let's just start coding it, and then maybe once you code it, then we can go back and I'll ask you
Yeah.
like based on your code.
Okay.
Or yeah. So yeah,
Cool.
let's start
So
coding it.
so let's start with we're given a matrix and then the output. So we're given a def what is this called? Longest increasing path. We're gonna be given a matrix, and we're gonna be given a we're pretty much just gonna return some return. Let's return 0 for now. So what we're gonna do is we need to return the longest path.
Mm-hmm.
So pretend we were running this on print. Like this. We're gonna run it on like this matrix at first.
Sure.
Test 1. And I think I modified it, but 0, 1, 2, 3. 1, 2, 3. So the result here should be 5.
Let's see. Yeah. Yeah. That's good.
So we'll be given test 1. Print matrix. Make sure this function is working correctly. Oh, shoot. Okay, cool. So what we're going to do is, let's see. We're given this matrix. So what I said is we're gonna want to loop through each element here. We're gonna want to loop through each element and try to do that backtracking algorithm on each element, or the DP algorithm on each element. For each row or column, we're gonna ask what's the longest path that we can get there, and we're gonna return the maximum of that starting. So we're gonna say what's the longest starting from here? What's the longest starting from here? Because we don't know which one. Where's the start of the longest path?
Mm-hmm. Yeah, makes sense.
So we're gonna go for row in range length of the matrix. That's gonna give us the rows for column in range length of the matrix 0. That's gonna give us the columns, and then we're gonna perform some DP algorithm here. What we're gonna do is we're gonna have a result here. We're gonna try to maximize, so we're gonna start with a float negative infinity.
Mm-hmm.
So what we're gonna do is we'll say result or DP result equals, we're gonna call the DP function on the matrix. and we're gonna pass in probably like a start value. But first, so I'll figure that out in a second. But what we're gonna do is we're gonna update our result, and we're gonna take the the maximum of the current result and the DP result. So the way we're gonna break down this DP is we're gonna have our base case that we're gonna probably handle memoization, handle if it's already in cache. I mean, like if it's not in cache, we're gonna recurse. Otherwise, recurse and store best result in cache. So we're gonna break it down into these steps. So we're gonna be given the row and the column, and then we're also gonna need to know. I think that's all we need to know right now: the row and the column. So what we're gonna do is, what's the base case is like if the row is less than 0. So first we need to capture out of bounds cases. I'll handle that in the base cases here. So I don't have to handle like looping through the neighbors smartly. But I'll do if the row is less than 0 or the row is greater than equal to the length of the matrix, return 0. And I'll do the same thing for the column here. So if these are out of bounds, if the row, and then we'll also say if it's out of bounds, we return 0. If the matrix at the row and column is not equal to, we need to give it some target. Is not, if it's less than or equal to, because you need to be increasing the target, we return 0. So that way, I mean, we don't want to keep looping. Like when we store here, we're gonna add 1 to our best result. But what we're gonna do is, if the matrix at the specific row and column is less than the target, then we want to. That's also a base case. If it's greater than, what we're gonna do is we're gonna return 1 plus like our best result, right? But what we're gonna do is we're gonna loop through our neighbors, so we're gonna get, or we're gonna also store our cache here, or our DP array. But if row column in cache, return cache row. Is it making sense so far?
Yeah, I think this will actually work. I think this is fine. I was gonna ask about like the target. Do you need it in the cache or not? But I think this works. Yeah, I think this works.
Or like we could even be smart with how we loop into it. Like we might not need to do this, but we could just like loop only if the conditions hold. So we can be like we can grab our neighbors. We'll just define some array here. Like row column. So we can look up, down, left, and right. So we'll go up, we'll go row minus 1 here. To the left is here. Down is here, and then, so we can look up, to the right, down, and to the left. So we can do for name row, name column in the neighbors here. Maybe what I'll do is I'll just add these. I won't add these in the base case. I just won't recurse if they're not in there, so I don't have to pass in the target.
Yeah, that's fine. Let me ask you just like a side thing, see if you know this one. So if you did put the target in the cache as well, if it was row column target, what would be the space complexity there, do you think?
If I had the target in there? Well, like the target is gonna be changing, right? So it's gonna it's gonna basically turn into like a 3D DP question because the cache is holding 3 parameters.
So if I'm on a cell, like let's say I'm on
Where are you? I'm following you now.
okay, yeah. Let me scroll down. So let's say we have this test one. Like let's say we're on this cell. What can the target possibly be?
If I'm on this on 9,
Mm-hmm.
yeah, we could have came from 0. We could have came from 4. We could have came from 9. So we could
Right. So how many values can the target have?
maximum 4.
Yeah. So what you're doing is fine, and this is like probably the approach I would take. But if you did actually store the target in the cache, and the important to recognize in these DP problems, it can't just be like any value. So it's not going to be like 3 DDP. It'll be like row times column times 4, which will be basically the same thing.
I see. I see. Okay, so it's not like it's not messing up the space too much. Like it's still
exactly.
the same space.
But I would take the same approach you're going with now, so it's totally fine. So
okay, cool. So if the neighbor row right here, Jan was good. No, we'll continue here. We continue here. So we say if the matrix at the neighbor row and the neighbor column is less than or equal to target, we just continue to. We don't want to go through that.
Mm-hmm.
Otherwise, what we're going to do is pretend there's no longest path, like they're all 9s. Is the result still 1? They're all 9s?
Yes.
Okay.
Should be 1 for that, yes.
So what we're going to do is we're going to do best result float negative infinity here. So what we're going to do is best result equal, or what we're going to do is like the max or the best result here. But eventually we're going to return that here. But what we're going to do is we're going to do, we're going to actually store in our cache the row and a column equals to like the best result if we start from our neighbor.
Mm-hmm.
Something like this. And actually, we're going to want to store this in a tuple. Cache it here. So, okay. How do we do? And then we're going to call the DP here. We're going to do DP. And we're going to pass in the matrix, the neighbor row, neighbor column, and the cache. So, yep, that's going to do the recursive function for all the different neighbors that are valid. And then we pretty much just need to do the same thing here. So we just pass in oh, we don't have target here anymore, but what we're going to do is instead of target, we say matrix, row, column. So matrix here, we're going to pass in the row, column, and then we'll just pass in like an empty. I mean, do we care about the cat? Or I'm just wondering if we need to keep the cache out here. I think we need to keep the cache, a global cache across this whole iteration. Because if we, because if we store the results.
Yeah, like what would happen if you initialize the cache here? Like if you just say like, every time I call DP from down here, I'll make a cache. What would happen?
Then like the cache will get cleared for every iteration we waste, like pre-computed results.
Yeah, exactly. Yeah.
So matrix.
Yeah, so every time you go through the matrix, you're gonna build the whole thing again.
Mm-hmm. That's gonna be a waste for sure. So we have cache right here, and then I think literally this code might work.
Okay. Yeah. Yeah. Let's not focus on running it on LeetCode. Let's just see how the examples go, and if the examples are good, we'll call it there.
Key year 0. Line 52. If the row column in cache. Okay. cache. Negative infinity. What do we maximize here? Best result. Maximizing here.
Okay. Yeah. So can you see what could happen that would be problematic?
Okay. Let me look through this code. So we're looping for every row in the matrix for every column. We're doing DP on our matrix row column. We're passing in our cache. Mm-hmm. The result, assuming the maximum is higher than this. Yeah, like if it even can't, like if it can't get any of them, the float will be negative infinity here.
Mm-hmm.
So like let's just say 0. So that's the worst case. 0 means you can't like we are at one element, but we can't get to any of the neighbors. So that's gonna be 0.
Yeah, makes sense.
Nice, cool. That returned 5.
Okay, so let's try a couple more. Let's try example 2 and maybe some other things that you could think of that would be like tricky, I guess.
What about that? How is that? That makes sense. The solution there, like.
Yeah, no, what you said makes sense. Yeah, so let's try example 2 and let's see if you can come up with anything else that is like, or let's try the rest of these, I guess, and see if you get the right stuff. Then yeah, if you could think of some other thing that you didn't test for, that would break this, then that would be good.
So if we do this breaks. Okay, that returned 4. That's good.
Mm-hmm.
Just like, I mean, we could start result at 0 here instead. Like if they give us empty.
Yeah. Yeah, that's the other thing I was going to say that would break is if you pass in an empty matrix, your stuff would break. But I think this handles everything now. So. Okay, yeah, cool. Okay, yeah, so what do you think about that one? I don't, like, it's like I said, it's a hard on leak code, but I don't think it's, like, that difficult, so.
But yeah, I think that was a interesting one. Yeah, it was, I think it made it easier that it has to be strictly increasing for sure. So.
Yeah.
But yeah, I think it's definitely, it's a good question for sure, because you can't just backtrack it. I'm pretty sure TLE.
Yeah, with TLE, yep.
But yeah.
So you recognize that like backtracking wouldn't be the best because you can't have a loop. So yeah, exactly, and you can cache results.
Yeah, like the part that I was thinking about is okay if we do DP, the one thing too though is like we also need to know what elements were used, because if we store a cache, right, the longest that it can go from there. Like it also took some path to get that result. But the reason why it's strictly increasing is the main reason. Yeah, I already knew it was DP, so that's the thing.
Yeah, so maybe if I didn't say it was just like you can do whatever you want, then maybe someone could land on a backtracking solution, and then I'd probably have to say like, can we do better?
Yeah.
Because backtracking would work, obviously, but
it'd just be super slow.
It would be exponential, and if the matrix was big, yeah, exactly. Let's try.
I think it's a good question. Like it's different because you have to loop through each of the indexes and try to go from there. So.
Yeah.
All right.
Let's try one more. Let's see how this one goes.
How long was that? 24 minutes.
Yeah, no, I do think that's like a pretty solid medium. If I had to rank it, I don't think it's that difficult. Honestly this one's harder, and this one's a medium as well. So in my opinion, anyway, we'll see how it goes.
Okay, so we're given a set of distinct thoughts on algo map. What's algo map? Never heard of it. Okay, let's read this though. Alright. We're given a set of distinct positive integers nums. Return the largest subset answer such that every pair ij of elements in this subset satisfies this. Answer I So for every I and j, if you mod them, you get 0. The values. Like either one, like this one divides j perfectly or j divides I perfectly. If
And this was
they're
also a daily problem like a few days ago, so if you've done it, we can do something.
no, I don't do the daily problem.
Okay, cool.
I should probably start, but I'm lazy to do those.
I mean, it's not necessary. Like, unless you're like making videos on them, you can do whatever you
Yeah.
want. It's not like it's better than something else.
Okay, so we're given. There are multiple solutions. Return any of them. So 1 and 2. Given. Okay. This is interesting. So the largest subset is 1 and 2 because 1 and 2 1 mod 2 is equal to 0.
2 mod 1 is equal to 0.
2
So
mod
it can
1.
be one or the other.
1 and 3, like return the largest subset answer, such that, like here, what I'm trying to figure out is why is it not, like why is 1 and 3 not there? Isn't, if you do 1 mod 3, that equals to 0, isn't
Yeah,
it?
so they tell you 1 and 3 is also valid.
But why not 1? Oh, okay. What? So the output can't be 1, 2, and 3 because 2 can't mod 3.
Yeah, exactly.
2 can't mod 3. So what I'm thinking is... That is a good question. Let me think. Like, at a high level, this is what I'm thinking off the... Like, it's a bit skipping ahead, but what we're gonna... Like, what I'm thinking is we want to be built... Well, first off, what's the brute force?
Mm-hmm.
I mean, it would be... Brute force would be generate the subsets. Like all the possible subsets. That's already pretty inefficient. O of 2n.
Oh, I see. Literally make every single one. Yeah, you have to make every single one, and then you also have to double check them for validity.
Yeah, and then like...
So it'd be like O of 2 to the n times n or something.
Yeah, exactly. Validate each one.
Mm-hmm.
But
Yeah,
what
definitely not an acceptable answer. Yep.
Like what I'm thinking is maybe there's a solution like this, like where we like hypothetically try to extend some subsets. So we have like some subsets where we know the length of those subsets, and we have like some hypothetical subsets. And then we know like some hypothetical subsets that are like that are marked by something. Either like it might be some value that encapsulates like who can extend this subset, right? Subset and size of the subset. So pretend we have one. We have no subset, so maybe we can start a subset with just one.
Mm-hmm.
As a count of one. Then we see 2. I mean, 2. Which subsets could it extend? It could extend probably this subset, and it could start its own subset too. Something like this. And we still have 1.
Mm-hmm.
So 3 comes in. 3 could pretty much extend this subset. It'll create its own subset with 3. But it'll be a size 2. Then it's kind of like the max of what we see there. Like what we can do is we can try extend. Like we can add it into subsets. Let's see. Yeah, something like that. But then pretend there's a 6 that comes in. Like we'd want to... The answer would actually be 1, 3, and 6. Or like... Pretend there was 9 instead. The answer would actually be 1, 3, and 9. So what I'm thinking is that's sort of my intuition for the problem.
And so let me ask you, like, so when you're saying like 6, like how do you know where you can add the 6? Like, how did you know you can add a 6 here? Like, what are things you consider, I guess?
Probably what I would consider one thing is maybe the largest value in there. That it could, if we could divide that.
I
The
see. So you
largest.
have like an increasing subset, and if your new number can divide the largest value, then you can add it in. And why is that? Why like if I had an increasing subset and my subset can just divide the largest value, how do I know the rest of them would work as well? Can we have a counterexample, or does that just work?
There might be a counterexample because if the largest value is 9, pretend the largest value is 3.
Mm-hmm.
No, that might just work. No, it might work if the largest value can divide my largest value or something like that. Or like pretend I'm looking at 9.
Mm-hmm.
Like if something could divide 3, it could also divide 9, I'm pretty sure. Because then you could just multiply it out by 3. It's like some math there that might make it work. Like if something is divisible by it can divide the multiple, then it could also divide. Like if 9 is divisible by 3,
Mm-hmm.
maybe from transitivity, I don't know, if 9 is divisible by 3 and something divides 3, I mean, you could just divide 3 times. Like it could break this up. Like if it can break this up into like what into terms, like you know what I mean?
I
plus
see what
t.
you're saying. So if you had a 9 here, if 9 can divide the 3, the 9 can divide the other numbers because each number is a multiple of the one before, I guess.
Or yeah, like well, if the largest element here can divide the new number we're bringing in, all of the numbers under it can also divide it.
Yeah.
Because it'll just divide 3, and then like it'll do that x more
Yeah,
times.
so if we tried to add another number here, like what would we check for?
First we'll sort these elements. Right? We'll sort these elements. These nums, but the number that we're gonna try to extend is like 3.
Like what's a possible number we can add? Like let's say we have this array. What's another number we can add after this that would work? Like how do we know exactly?
18.
Yeah. Okay.
Yeah.
Yeah, so because it divides 9, it divides the other numbers because each number is like a multiple of the one before.
Yeah, exactly. I think that would work. Let's
Okay,
see.
so if we go with this approach, like let's say we're just keeping track of subsets. First of all, do we need to know like what is this, the count or the length of what does this number represent? The length, I guess.
The length, yeah, the length. These are the lengths, so this would be 3.
Okay. And so your approach is like once I'm on some number, I'll just try to extend every subset I have by checking the last number. So like let's say we have like a big array and we're close to the end. How many subsets can we have already? Like if we do that approach where we just take our number and we just check like does it extend every subset we have? Like what would be the time complexity for that?
Well, we can just check our multiples. Like, wait, let's see.
Right. But for every subset, we still have to check the number, right? So if there's like 1,000 different subsets here, and we're on some number, yeah. Like let's say we have 1,000 numbers, and we're on number 1,000. How many subsets can we have already? Like, can we have 1,000? Can we have way more?
Yeah, we can probably have like 1,000 if we just choose really like a bunch of prime numbers, something like that.
I mean, like worst case. Sorry, worst case. Yeah.
Wait, can you repeat the question? I'm a bit confused of what you're asking.
Yeah. So if we just have like a bunch of numbers here, right? Like 1,000 numbers, and we're on one of the last ones, and our strategies for every number, let's just compare it to all the subsets we already have. Once we're on this last number, like how many subsets can we have already?
Well, we're not gonna like what we're gonna store is like if we can extend one, multiple one, we can have as many subsets. Like
I guess let's just walk through like the dry run for this case, for this 1, 2, 3, 9. Like how would this work?
Like
and how many would we?
What I'm saying is it could either be exponential the amount of subsets if we're gonna store every single one of the subsets, or it could just be if we find a smart way to remove subsets once we extend it, it could just be like O of n size to look.
Yeah. So is there a way we can make it like with this example, let's try to figure out a way to not store every subset, because here, like, we can have one, we can have one, two, we can have one, two, we can have one, two, three, we can have one, three, and so by the time we get to this 9, we can have more than 3 subsets, right? We can have like some exponential amount if we store all of them. Like 1's a subset, 2's a subset, 3's a subset. 1, 3, 1, 2. You see what I'm saying?
Yeah.
It's not like linear. So how do we optimize that?
Wait, sorry, could you repeat that? That part?
Yeah. So for example, like if we just store all subsets, like 1 could be a subset,
Yeah.
2 could be a subset, 3, and so on, right? 1, 2, 1, 3.
Yeah, that's exponential for sure.
So by the time we get to the 9, there won't be 3. There might be, like a lot. So if we take that approach where if we just, even if we're only comparing to the last number, if we compare our 9 to every single subset we've made to see if we can extend it, that's still going to be exponential, where essentially for every number we have to compare it to some exponential. So that might be like n cubed or some whatever. So can we optimize that where we don't have to compare it to every subset?
What I'm thinking is, like, if we could extend one, we can delete the other one too. So pretend, let's start with 1, 2, 3. Let's say maybe we have a hash map. And then first we have 1, and that gives us that doesn't work because it needs to be returned large. Like, does 1 just work, or if 1 would return 1, the subset of size 1? I mean, it needs more than 2 elements, right? At least.
It can be 1, I guess, technically.
Okay, so we have 1.
Like if we have an array of one number, we'll get 1. So yeah.
Okay, so let's like loop through this right here. And this is one where I can't think of a top down right off the bat. So if we do 1, pretend we have 2. For 2, we could extend. If we have 2, we could extend. We could extend 1. But how do we know that? Well, we could loop through all the answers here, and then we can go 2. 2. We can get it to 2 elements, right?
Okay.
Oh no, but we need to output. Do we need to output? Oh, we just need to output the size. Okay.
No, we need to output the whole subset. But let's say we only needed to output the size. How would we do that? Like, let's change the question a little. Like, if we just needed the size, maybe we can do the subset as a follow-up.
So if we need to output the size, we do 2 and 2 right here. When we have 3, we can loop through the values here and see which ones we could extend, and then we can add 3 and then 1 here.
3, 1.
Or sorry, 3, 2, because we could extend 1, but we'll try to extend like the largest one that we're divisible by.
Okay.
Then when we get to 9, but yeah, it will be like a O of n squared algorithm. And we do for 9, right? Who can we extend? Well, we can 3 can divide us. So if we add 3 there, or we can get to like 3 here. Right? And then we just return the maximum of this. But we'd still have to loop through all these values.
Right, so what would be the time complexity of that?
O of n squared, pretty much.
Yeah. I think that's good. And then, so I'll give you a small hint, because we've only done top-down. So for rare problems, bottom-up is actually better. So whatever you prefer, I guess.
Oh, for array
Most
questions,
of
you're
the
saying?
times-
For array
What was
questions?
that?
Array questions, top-down
Not
is easy?
necessarily array, but kind of like with this approach, for every number, you're checking your output you built before. So if top-down makes sense, you can do top-down. But in some cases, bottom-up like just intuitively makes more sense, which I would argue this is one of them. So, but if top-down's easier, we can do that as well.
Yeah.
So yeah, I guess.
Does this...
bottom-up is literally just like, you build an output like you were saying, like basically what you described. So.
Do you think this solution is gonna work, or we're going the right direction here for O of n squared? We can.
I think this is literally the solution. Yeah, so I think it would work.
But this will just return the size, right? Not the actual output.
Right. So I'm saying let's code the size and let's do like a follow-up.
Okay.
The actual thing.
Okay, yeah. Sounds good. Yeah, this is a good question. Is this medium?
Yeah, it's medium, but I'd say this one's harder than the one before. For sure.
Okay. To get subset size. We're given nums. We're given a distinct positive nums. Return the largest subset answer. Okay. So what we're gonna do is we're gonna be given like we're gonna have a path map. This is the same or subset map, and we're just gonna return the largest value. We're gonna store the longest or the largest value of each one, and like the size. Maybe we can use a default dictionary.
Sure.
Or no, let's just do this for now. But what we're gonna do is like for num in nums. Like I said, we're gonna sort nums first. That's important part. So we're not. That just helps us like we know. Like pretty much, it helps us get into allow us to just compare. Like when we're looking at a value, we know all the subsets that we're trying to extend are less than it, so we could just do one equation there.
Yeah.
So for num and nums, what we're gonna do is like if we're gonna also loop through all the elements in this subset map. So all subsets equals dot keys, I think.
Okay.
So this is gonna return the elements in the subset, like 1, 2, 3, 4. Sorry, let me just list this out. So now we're gonna loop for num in nums. What we're gonna do is like, is it actually divide is for subset key in is divisible. We're gonna take the subset key, which should be an integer. Hopefully, let's see.
Yeah, I think it just stores as a key in Python or as an integer already in Python, even if it's a key. So I think you're good.
So we're gonna say is divided by the current num equal to 0. And we're gonna have our best result here. We're gonna try to maximize it, right? So 0. If it's actually divisible, what we're going to do is we're gonna do best result equals the max of the best result here, and what we're gonna do is we're gonna grab all subsets, that subset key plus 1, because that's like I'm extending it. And then we'll say subset map equals the best result. Subset map of num. Something like that. So we sort the nums. We're looping through all the keys. So let me just walk through the example and then I'll try to catch anything breaking in my code here. But what we're gonna do is we start at nums equals 1, 2, 3, and 9 here. And let's start empty here. So we start at 1. Now it's sorted for num and ones. If the for all subsets, there's no subsets, so it doesn't even loop through here. So 1, the best result should actually just equal to 1 here. Right. So we're trying to maximize.
Yeah.
So 1 equals 1. Okay. And then when we get to 2, we for 2, the best result here, we're gonna loop through all the keys. So it's gonna loop through 1 here. So is 1 divided? Can 1 divide 2? Yeah, that's divisible. So we could extend here. So if we print the map, we should add like 2. Should be 2. Let me print the subset map. Let's just see if it it creates the right subset map. Oh. Print sub. Alpha, you still there? Or your
Yeah.
dog?
Nah, yeah, I just have dogs in the background, so I muted my mic. Still there. Okay, so do we have the right thing? Not quite.
Subset of num equals the best result. All subsets of the subset key. Okay, let's print it for each iteration.
Sure. Like, I think you're on the right track. You just have some syntax stuff.
1 1 2 1. Okay, when we put 2, if the subset key, let's just make sure it's actually going into here. It should in the first one. Okay, it's not. So if the subset key mod num, what's the subset key here?
Yeah, I think you'll figure it out from here.
1 divided by 2. There's no remainder supposed to be.
You did 1 divided by 2 instead of 2 divided by 1. So you just need the
Oh yeah,
rest.
you're right. Yeah, 1 divided by 2 is 0.5 is the remainder.
Mm-hmm.
The keys are not
You have a comma here.
Oh yeah, you're right.
I don't know if you have anything else, but the keys is not subscriptable.
Oh, also. Oh, I just need to turn this into a list.
So you can just do for key in dict. That would give you all the keys too. You don't need this.
Okay, look at this, right?
Yeah, and you get rid of that completely. So subset maps should just be your map.
Yeah. Okay. This one. All subsets not defined. We just just fix this.
Yeah. Okay.
Holy.
Yeah, you can just iterate through keys. Okay. Okay, I think we have the right thing now, right?
Yeah. Returns the right result there.
Mm-hmm.
So what I do is actually we'd have to do some copying.
Yeah, so what are your thoughts of how we can get the actual path? And we can't, remember what I said, we can't store every subset because there's just way too many. So how can we kind of efficiently build a path?
Let's see. Like what we can do is maybe encode it in here.
I think your stream's like lagging in your
Oh, really? Am I?
Yeah. Stream is like frozen. Yeah, I think
Wait,
stream's
let me check,
frozen,
let
your
me check.
voice is lagging.
What the heck? Okay, give me a second. Stream, is everything good? Probably tweaking. Yeah, stream rate. One sec. Like, this Wi-Fi is trash out here. Okay, it's lagging. Okay, give me a sec. Let's wait until it's good. Good thing I recorded this too.
Yep.
See if it's still live. I'm gonna pause the recording. Let me start the recording. So what I'm thinking is maybe we store the subset here. Like in a tuple, we say this is 1. When we store 2 here, we figure out a way to extend it.
Yeah, so is there a way we can like not store the whole subset everywhere? Because they can get really long and we want to store them everywhere and that would also be expensive. So is there like another way we can kind of store like what's the minimal information we need to be able to build this?
What if we just store who we extend? So we extend 1. Then
Yeah,
we could just
exactly.
we could just like rebuild it after.
Exactly. Yeah. So let's go with that. Where like we just keep storing who we extend, then we
Yeah.
rebuild at the end. Yep.
Holy crap. Okay, this question is good. So if we like extend 2 here, like pretend.
Yeah, I think this is a pretty good question to be honest. And this is a medium, so yeah,
That's a
I don't
wild
think it should be a
medium.
medium.
So what we'll do is we'll say it'll just be tuples, and we'll be like we'll extend none, nobody, like this ourselves.
Mm-hmm.
This one will extend 1, like our largest. Here we'll extend 1, which is our largest. Here we'll extend 3.
Yeah.
And then when we
then
build,
how would we rebuild?
probably we'll just like keep following it. We'll be like, okay, this is we start with 9.
Mm-hmm.
Start with 9. We could return the list in any order, right? 9. And
No,
then,
I mean you can just reverse. That doesn't matter.
that's true. We grab 9, and then after we grab 9, we grab 3 here, and then we get the element 3, and then we grab who this extends, which is 1 to get that. Like we just do a while loop.
Mm-hmm.
So best result, but here we need to store the best result is gonna be equal to 1, like none, something like this.
Mm-hmm.
Let's see, 1 none, and then so the best result equals if and let's see, okay, we just need to extend this part. So the best result is a tuple now, so we can't just do this, but we can clean this up in a second, but I'll add a second loop. We'll say if the subset map or maybe we'll just start this with like 0, but the best result is 1. Oh no, we can do 1 here, but if this result is greater than or equal to, or if it's less than equal to, like we don't want to extend it if it's not best than our best result, right?
Mm-hmm.
Otherwise we'll do best result equals, what we'll do is subset map here.
Mm-hmm.
And then who did we come from? We came from this subset key. And then we'll store that in the best result here. But now we need if the subset map subset key. And then we just need to best result 0th element here.
Mm-hmm.
So we're comparing the values, then we're good. Let's see how that prints out. Print subset. Still none here. Subset key. If, okay, let me figure this out. If the num, so we're looping through numbers and numbers here. We're given the best result 1. We're given none. If we're looping through the subset keys, which is 1, 2. If it's divisible by 0, if the subset map, and then we grab the subset key, we grab the 0th element. If it's, let's say if it's less than, oh no, we're not plussing 1, are we? Best result.
No.
Yeah, we have to best result. We have to add 1 here.
Okay, makes sense.
I think that should work. Damn, there's like an off by 1 here.
Mm-hmm.
Is it less than? If I trace it, it'll probably work. But okay. Let's see. Where did that fail?
63.
Subset. Oh no, it's up to 0. See what I'm doing here? Okay, there. Now that works.
There. Yeah, nice. Okay. No, yeah, I just didn't want to look into it too closely. Like from here, it's basically just like debugging. You get the idea. Yeah.
So what's our best result? Print subset map. Our best result. I mean, let's just find it. Or best. Let me think about it now, because now we just need to rebuild the subset.
Mm-hmm.
I mean, we could do one pass to find the best result, and then like do a while loop.
Yeah, exactly. Like we could just find where to start from and just kind of do like a chain.
Yeah, so we can best result. I mean, we could store that here too. We can just store.
I see. Have
Start.
another variable.
Start is equal to like none and none. Or we'll just do like float negative infinity and none.
Mm-hmm.
So we'll say if the best result, like the 0th index, is greater than start at the 0th index.
Mm-hmm.
We'll start from this one instead.
Yeah, that makes sense.
Then we'll just like print start here. We could like keep 3 and 3, and we'll say while start.
So we need the key as well for the 3 and 3, right?
The key.
Yeah, like because the key, or you got 3 and 3, but what value was that? Like you need to know that it starts with a 9. Or
Yeah.
you could compare values or something, I guess. You could do
That
that
makes
too. You could
sense.
like say like this is the value I need, whatever key gives me that, let's go with that. Yeah.
But okay, if we're given 3 and 3 here, that doesn't tell us much, just the value and the actual key there. Then we need to store another value in here. Result.
Yeah, we need to store the key.
Yeah, best result. The num here. Num here.
Okay.
I have to keep running this one, 3, 9.
Yeah. Okay.
We'll have a result.
Mm-hmm.
We'll return our result, and we'll say while start 1 actually exists, we'll do result dot append start the value start. So the second index, we'll say start equals subset map. Subset map. What are we storing in the subset map? The keys. So
Yeah, I mean, I think if you just traverse through the keys, that will work.
start 1 like this.
Like 9 will go to 3, will go to 1. So you just start can just be the key. 9, 3.
Oh wow, start is. Oh no, because it's off by 1. Then we'll just do start at 2.
Okay.
That just captures like when it dips out the.
No, yeah, I see. Yeah, okay, looks good. And then you just reverse. Yeah, I think the actual problem asked for the numbers in the same order as in the array, but that's like 2 more minutes of code, so we don't need to do that because all the numbers are unique. You can just store the index or whatever. That
Oh,
part,
okay.
who cares?
Nice. Reverse.
Okay, yeah. Okay.
Yeah, that was actually low-key hard. Let's see, 139.
Mm-hmm.
That's very different than the DP ones I've ever did.
Yeah, so that's what I kind of wanted to do this one. So I was either gonna do this one or like a regex. A regex is top down, but it's just like pretty complicated to get all the edge cases.
Mm-hmm.
So yeah, so for some problems you will realize that like bottom up just makes more sense. Like I'm just like iterating backwards or something. So then So then bottom up makes sense. Also, this one there's the tricky part of like rebuilding the path, which is pretty
Yeah.
rare.
Rebuild the.
Like they don't just give you a number. So yeah, usually the way to rebuild the path is you figure out like what's your end, and then you cache everything else, and then you just do like you basically do like a DFS or whatever, like
Yeah.
towards the front. So that's how you would do it. So there are some problems that ask you that where they're like, don't just give me number, give me the entire path of like the best thing, and that's how you do it. You'd like split up into 2 parts.
Damn, I need to do this question. Any advice on how did that session go?
Okay, so let's see. So the first one you were able to do basically no hints, I feel like. Which is stuff you've done before. This one, there's a lot of new stuff thrown at you, right? Bottom up, you haven't done, and rebuilding the path. I feel like with the hints, you were able to do it. I think this is honestly a pretty hard question. Like I said, it's a medium, but I think if you've never done bottom up or not often and never done this kind of thing, I wouldn't expect you to get it. So I'm pretty happy with what you did with the hints, and I feel like if you see it again, you can kind of be like, oh, I've seen this kind of thing. The really common question you get asked is like longest increasing subsequence.
Yeah.
Which is kind of like this, and then you would also do that in bottom up, because it makes more sense. And you kind of do the same approach. You don't store the entire path. You just store like, what am I building off of?
Nice.
Yeah.
Yeah. No,
So,
there was a bit of math involved too. It's like the divisor thing. I had to do a little bit of thinking for that.
Yeah, that I feel like if you just do enough leak code, all the mod stuff you just learn. Like I learned like modular arithmetic, all the like tricks. Yeah, like you're gonna be pretty good at that if you just do a lot of leak codes. Like I don't think it's like advanced math or anything. So
nice. Yeah. No, thanks for that. That was a really good session. Let's do another one like next week, or we'll just go even harder.
Yeah. So I think probably I'll just get some like really hard ones.
Really hard.
Yeah.
Where do you?
So the problem. So a lot of the problems is you will just not be able to figure out the state, and if you can't figure out the state, then we're kind of stuck. So I'm going to avoid those, but I'm just going to find ones with a lot of edge cases. Like the regex one, for example, has a lot of edge cases.
I see.
So that's a pretty good one.
Nice.
But yeah.
Where do you think I'm at with the DP? Could I pass a Fang?
Yeah, I don't think they're going to ask you this kind of thing on Fang. Like,
this
I
one's
think
too
they'll
hard.
ask you like coin change or whatever, or any of those. And those you can do fine. So I think this is like more advanced.
Nice. What about for advanced? Like, is this a pretty hard one or not? Like, or there's even harder ones?
I'd say it's a pretty hard one. Like I said, the harder ones are... Basically, the way DP gets hard is the state gets really hard to figure out. It's not something obvious. It's not like an index. So those are the hard ones. And also some, you have to optimize space or it'll get TLE. And those are like, that's like the really hard ones.
I see.
Yeah. Pretty rare. I don't think you get asked. Like, even if you know how to do it, the time it takes to code it, even if you know how, it takes like too long for an interview, in my opinion. Unless you're like a competitive programmer or something. So I don't know if they're like testing that.
Cool.
But yeah, I think this one is kind of probably the hardest I'd ever be expected to get asked something.
Nice.
So if you can do this one, if you can like redo it fine, and so it's pretty good.
Cool.
Yeah.
Yeah.
All right.
Cool. Thanks, Alpha. Let me know. Yeah. Just message me when you want to do stuff on your side too. If you want me to do more front end on you or like.
No problem. Like... Yeah, we can definitely do some more in the future.
All right. I'm stopping.